Hi everyone. Um, Basically, before around 6 years, I was working as a machine learning researcher, trying to solve cybersecurity problem using machine learning. And then one day, my professor came to me and said, well, you know, we have this great project with a big company, but the challenge is we're going to use petabytes. So I was like, machine learning, running statistics, trying to be as accurate as we can, and then running it on petabytes, it's not going to work with the usual tools that we have. So I had to jump in and say, OK, I'm going to use big data frameworks. And as you all know, it was a few years ago when Spark wasn't really a thing. So we need to work with MapReduce, and Hadoop, and Hive, and Pig, and all this kind of stuff, which actually led the way for me to start working as a data engineer and better know what is data engineering means. And I got really passionate about optimization, about what's happening behind the scenes, about distributed systems, about all this awesome stuff. And actually, I spent so many years, enough years, weekends, holidays, and all this kind of things trying to solve production issues, working with Spark and working with Kafka. So I hope today I'm going to give you some input about the things I learned along the way so you can be better and more successful and have a more efficient work with Apache Spark. So that's me. I'm Adi Polak. I recently joined Microsoft as a cloud developer advocate. The reason I did it is because I'm passionate about the cloud. I used to work mostly with data centers that we had, and I think the cloud is definitely the future. So if you're interested in learning about it, there's tons of information online. And to our agenda, what are we going to do today? So today, we're going to work with Apache Spark version 2.3. We're going to understand what catalyst optimization is. We're going to understand what is UDFs, what does that mean, what happens when we use UDFs, and we're going to talk about cost optimization, because at the end of the day, we care about money, we care about time, we care about our users and customers, and how we can make sure we're delivering our outcomes. So are you ready? Yes. So just a basic concept before we start. Apache Spark is a distributed general-purpose cluster computing framework, as we all know. The Catalyst is the heart of Apache Spark. It does all the heavy lifting. It's basically the SQL engine behind the scenes of everything we do. It's the SQL optimizer. And we have the user-defined functions that basically help us make and add more functions into the Spark SQL DSL that a lot of people use. And we need to know how to use it the right way, and we're going to talk about it. So who here uses Apache Spark on a daily basis? Cool. Who is a data scientist interested in integrating Apache Spark? Who is a data engineer already working with data? It might be Apache Kafka. It might be all these other things. Cool. And who is a business analyst trying to find the next insight that's going to make a lot of money? No one interested in money? OK. That's fine. So when we talk about Apache Spark, basically, there's a generic architecture that constantly repeats itself. Here is an example about how you can do it in the cloud, but basically, it doesn't matter. You can use any cloud you want or any data center you want. But the thing is, you always need to get data into the system. We always need to find it can be either structured or unstructured data, but it doesn't matter. We always need to ingest more and more data, keep it in a specific storage, and then analyze it using Spark or different frameworks. But here we're going to talk about Spark, and then get the insight, put it into some dashboard, or send it into to our clients and work with it. So it doesn't really matter your framework or where you're installing that architecture. It's often the same, and you'll see it continuing again and again when you work with it. So what is Apache Spark? Apache Spark is basically a group of layers that build on top of each other. And what most users first see is the two layers at the top. So at the top, the first layer is the API that Apache Spark exposes. It gives us the streaming. It gives us the machine learning libraries. It's a limited machine learning libraries, but it's still nice to start working with it. It gives us the graph frame, and graph frame basically helps us calculate graph at distributed manner, which really helps us if we have like huge graphs, like if we're working with social media content. And also tensor frames. Tensor frame are basically TensorFlow on top of Spark. There's not a lot of content online, so I created a few blog posts for it, because it's super interesting how you can work with TensorFlow on top of Apache Spark and really optimize it and get everything you want from it. So if you're interested, definitely go and check it out. And then underneath, we have another layer that also we can use, and that's the API of the data frame and the datasets API, and also SQL. We can just write SQL the old-fashioned way, the way we know and love, and Spark will know how to digest it and how to run it for us behind the scenes. And then we reach the heart of Spark, the optimizers. So we have the Catalyst optimizers and the Tungsten. The Tungsten do the low-level heavy lifting, making sure our hardware is fit for the mission we're giving it. And then the Catalyst try to optimize our queries, try to take whatever we want to do and put it in a way that it's going to be easier for the CPU, easier for the distributed systems to do it. And underneath that, we have the connectors and the storage itself. So basically, Spark is an engine, but we need to give it the storage that we want to work with. And for that, we have the connectors. And the connectors, it's our link to the storage. We're going to tell them, OK, I would like to work with Parquet. I would like to work with Hive. I would like to work with Cassandra. I would like to work with all these databases. And we need to make sure we're configuring the connector right, so it knows how to use it. So how do I do it? I mean, we said we're going to do optimization. How do I optimize? So 1 second before we're jumping into optimized, let's understand the flow of the Catalyst optimization itself. So we said we are exposed to we can write the SQL query, the data frame, and all those kind of APIs. So what happens from there, it's all translated into unresolved logical plan. So at this stage, we don't know anything about the data. We don't know anything about our query. And then we get the catalog data. And the catalog data holds the metadata for the table that we want to work with. And it's part of the analysis phase. So then it combines all the data together, and it put it into analysis. So now we actually know what features we have, what kind of feature, if it's a string, if it's an int, and all this kind of stuff about the table, where the file is, what kind of storage we're using. And then it moves to the optimization phase. And the optimization phase is the most important phase in here. And then it gets the physical planning. And the physical planning creates us multiple plans that we can use. And after we get the multiple plans that we can use and we can run, it sends everything to the cost model. And the cost model is available from Spark 2.2, and we're going to talk about it as well. And then it says everything into the code generation, which later distribute the output, distribute the bytecode that we got from the code generation into our executors to finally do the job and run the tasks that we want. So how does it work behind the scene? How does the Catalyst Optimizer work? So it creates a tree of all the operation we would like to do. It's create a tree of all the tasks you need to do, everything it needs to run on every entry in the database that we're reading. And then it has a set of rules, saying, give it that kind of type of rule, maybe I can prune, I can cut the tree. I don't have to do all these operations. I can decide and do just half of it. So here, for example, I have some function in the leaves, and you see it in the purple-pink color, that was said, OK, this leaves can be replaced with a different function, and basically, we don't have to execute it, so we're going to cut it. So we notice how the optimization work. It basically cut the trees, and what do we gain out of it? What do we get? So Spark behind the scene implements a lot of optimization. It doesn't yet reach the level of a classic SQL database, but it's still work in progress, and they're working on it, and they did implement a lot of really awesome features, like predicate pushdown, like project and pruning, and all this kind of stuff. So I'm gonna talk a little bit about predicate pushdown because it's an extremely important feature. And predicate pushdown basically say, I'm not gonna do the filtering or the predicate or run this specific task over using Apache Spark. So I'm not gonna bring the data into memory and then run it. I'm gonna run it in the storage level, which means if I have a filter, I'm basically telling the storage, don't give me this specific data. And what does it mean for the storage level? It can mean that if the storage is configured the right way, we're not going to read those files, which means less I/O, less cost, because we're not reading the files, and less time spent on I/O and resources. So this is the predicate pushdown. And another one is the project and pruning. What's happened when we work with Spark? There's different operations that we can do. We have the action, and we have the transformation. And since Apache Spark is lazy, it's always go with the transformation first, but not actually creating the action, not actually running the query that we send it until we tell it explicitly, please run it. So it basically sometimes aggregate a lot of SQLs together, and it knows how to cut the parameters or how to cut the features that we're not really using. Maybe we're doing select star, but then 2 queries later, we're not really using the feature we're reading. So Apache Spark is smart, and it's lazy, so it tells us, we don't need it, we're not going to use it. So this is a list of some optimization that it implemented, but as long as we get new versions, it always adds more and more to it. And now we're going to talk about what is custom UDF. So it's a user-defined function that we can define. And how do we do it? We basically, this is a Scala code. We basically create a function. Here's a simple function that null, it's get a string, it returns a Boolean, and this is how you do it in Scala, and this is our UDF. And in the second line, we're registering it, saying, it's gonna be, this is my UDF, it's gonna return a Boolean, it's gonna get an input, a string, we call it with the string not null, and this is a reference to the function I'm gonna run. And then I'm writing a simple string, which is my query, select star from specific table, where not null about specific product, because I don't want to get null for this product. I want to make sure I have all the values around this product. And then I'm running it through SQL context and Spark sessions. But then I'm using the explain method. And the explain method actually shows me what's going on behind the scene, what Spark is actually going to run before it runs it, because it's not an action, it's only a transformation. So I'm using the explain method with true, and then I get, as the flow before, I get the first logical plan. So I have the project, give me everything, project star, and then I have the filter, not null, but as you can see, it's, as you remember, it's a UDF that we implemented. And then we get the analyzed logical plan, which we combined with the catalog. We finally know what the filter in the table. And under the filter section, you see UDF not null, and then we pay a heavy price with the casting. Because say, I don't know what I'm getting here, but anyway, this UDF is need to be cast. So even if I get a string, I'm going to cast it to string again, which we're going to pay a heavy price for casting. And then we get the optimized logical plan. And then we get the actual physical plan of what's going to run. And in the actual physical plan, we see that the filter is in the top. And then at the bottom, basically, it scans the data. And under push-down filters or partition filters, we have nothing, which means we're going to do a full scan of the data no matter what, which means we're going to use a lot of I/O, and we're going to pay a lot of money and time and resources doing that. So we don't have any push-down filters. So what are the optimization we lose when we're using Apache Spark? So we talked about predicate pushdown, and that we know, but we actually lose all the optimization that the Catalyst gives us. And why do we lose all the optimization that Apache Spark gives us? Because basically, if you look into the documentation, and they have a really, really long documentation, they say, well, we don't know what to do with it. It's a black box, and we don't even try to optimize it, so whatever, you know? So what can we do? I mean, we do really want to optimize it. We don't want to pay a lot of money, and we want it to be efficient and fast. So we use the Spark SQL functions. And the Spark SQL functions already optimized with the Spark engine, with the Spark Catalyst engine, and also sometimes with the storage. If you open Apache Spark open source and you look into the code, you'll see that it coupled really well with Parquet storage. So basically, every optimization that they can do specifically for Parquet, they did, and they're adding more and more features as long as Parquet progressing and moving. So definitely see if you can use those functions, and definitely see if you can find your solution there. And of course, if you can work with Parquet, it would be the best way to go. So where can you find these functions? You go to the documentation, you put in the version that you want, and then you add the API. Here it's specific Java, but if you want Scala, if you want Python, everything is available there. The function has a lot of different variety, like array, contains, filter, windows, strings, dates that a lot of people use, a lot of really cool functions that you don't need to implement at all by yourself. So that's cool, but how do we use the functions? So here's an example of how I took the previous logic and implemented with functions. So I took the Black Friday table that I work with, I call the filter function, and then I use a function on top of the column that I have from the API and told it, well, if it's null, just filter it, I don't need it. And then inside, after doing it, I can call, and remember it's lazy, it means it's not running yet, but I can call the query execution and get the information about what's going to be behind the scenes of the query, so I know what's actually going to run in practice. I can do that, or I can either do explain and get all the information. And just as a reminder of the flow, we have the first phase, which we call kind of the front-end phase of the Catalyst, where this is where we're working, and that's where the API we're using. And then we have the optimization itself, and then we have the backend. And the backend is where we send the data and the plan to the executors to start doing their thing. So what happens there? We had the parsed logical plan, and now it knows its isNull function. It doesn't treat it as a string anymore. Still not treated as a string because it knows what it is. Optimized logical plan, we see it again. And then we get the physical plan, where we finally get the push-down filters, which mean we're not going to read anything that has product category null, which means we might skip a few files if we look at the storage level, which means we're going to save a lot of money and I/O time and resources for a cluster, which means we can run more job and do things more parallel. And that actually means we finally know and understand what's happened behind the scenes, because many times when we work with Spark, we kind of run things, hope that it's going to work, but then we figure out it's not really work the way we expected it, and then we have to go back. So when we use explain, it actually shows us what's going to happen. So that's a great thing to have. So that was about the Catalyst, and that was about UDF and how we can work with them. But now let's get into the cost-based optimizer, which is a relatively new feature that was released in 2.2. It's still in disable mode by Apache Spark, and you can enable it. Just make sure that it does the work you expect it to do, because it's based on the information you're going to give it and the statistic you're going to give it. So let's look where it is. So this is the cost model, and it exists since Spark 2.2. And what it does, basically, it gets a lot of different physical plans and a lot of metadata from the storage itself, and then it tries to calculate the cardinality of the amount of data of the output itself. So it's trying to calculate how much CPU we're going to use and how much I/O we're going to use. And based on that, it tries to optimize which query to run and how to run it. So in order to get it, we first need to enable it in the configuration. And second of all, we need to run this query. So it basically collects statistics on the table or on the storage we give it. So it's analyze table, and then the name of the table, and then compute statistics are all saved words. So you can use them when you run your own SQL. But when you use it like this, it basically tells us, collect the statistics on the data that you have, so we can have a better queries. We can calculate the cardinality of the output, mostly for join operation. So we can predict and use a better tree, a better operations for it. So the types of data it's collected at the moment, and they keep on adding it. So it's mostly numeric, date, timestamp, and binary type. And the reason they do it, because they need to understand what's the cardinality. Like if we have a numeric, sometimes we can define a numeric as int. Do we really need the minimum int up all the way to the maximum int? Probably not. So it gives us the minimum and the maximum and the range we actually need, and then it can use a lot of different algorithms to optimize how it's collect the data and what it does with it. Same for distinct count. Many people do and run distinct counts or their queries. They want to understand how many features are there, what are they seeing. And here it's already built in. It's already part of the metadata, so we don't need to run, we don't need to do any calculation about it. It already exists. Same if we're working with strings. So here for strings, it collects the average length and the max length. And the reason it does that, because there's a lot of algorithms behind the scenes that helps us decide what's the length of the string we want. If we want to use like string buffer, or we want to use array of chars, or all these kind of things, that it can be more cost effective after when we translate it to bytecode. So what does it collect? What is information it needs, and what do we need it for? So it's really useful in filter selectivity. It helps us know if we want some values bigger, smaller, and all this kind of things. And then we combine it with the join cardinality of the data we need. So basically, we can predict what's going to be the size of the actual output before running our queries, which gives us a much efficient join, which is really the pain point of everyone who works with big data and data in general, or SQL. Even on a small data, try to run Cartesian join and see how long it's going to take you, even on a tiny file. So what about an example? See how it works? So let's say I have these two tables of employee and salary. I'm reading it from the database, it doesn't matter. And then I'm going to use some UDF just for the game. I'm going to call it start with A. And then I'm going to create my SQL query. So select employee name, employee age. And what I want to get is I want to get all the employees that their names start with A, and their salary income is bigger than 50, and their age is bigger than 18. They're 18 or bigger than that. So that's the query, that's what's written here. And now I'm going to run it. I want to see how Spark going to actually do it behind the scenes. So I'm going to jump into the physical plan. And what we see here, we see project, which means this is the features we're going to get back at the end after the query finished running. We're going to see a broadcast hash join. And why does it do a broadcast hash join? I didn't ask it to do any broadcast. And broadcast basically in Apache Spark means I'm going to take some specific data and I'm going to send it to all the executors who need it. And then they get the whole data there, and it's usually mean the data is small enough so it can fit into memory. So we don't need to distribute it. So here it decided to do a broadcast hash join. And the reason it decided to do a broadcast hash join because it knows the table is small enough to fit into memory. And actually when we're doing join that way, it means we don't need to do a lot of shuffle of the data, because we don't take chunks and shuffle it all together. We just send the small table to the rest of the chunks, to every chunk, and then it does the join there, and then it collect everything back in a reduced manner. So here we see how useful it is by changing it to broadcast hash join. But we still have the UDF, which means we read all the data. Although it's a small table, we read everything, and then we broadcast everything, which means we probably paid in network. So what do we do about that? We just use the column function that does the same thing, because we have a column function that knows how to work with strings. We have a lot of APIs of working with strings. So here we're just using the filter API, the join API, and the start with API that helps us get what we want. And then in our physical plan, we have the push-down filters, which means I'm reading a smaller data out of the storage. And then I'm going to do broadcast hash join of that small data, which means I'm going to use less networking, which means it's going to happen faster, and there's not going to be any bottlenecks on the cluster itself. And this is for us, when you work with distributed data, what we call rate success. So this is a job I ran over Databricks. And Databricks has all this as basically a software as a service, and you can use it in all the clouds. I use it specifically on Azure, but you can use it as well on AWS or on your own data center. And here, if we'll do a zoom in, you can see that the first one, I used the built-in functions. And on the second one, I used the UDF without any optimizations. And the one with the UDF took 6 seconds. Well, the one without the UDF and the optimization took 1 second, which is a really good improvement when we're looking at big data. Yeah. So more runtime benchmark that I ran. I worked with a few data sets to see how it works, and I tried the part of optimization and giving it all the metadata in the beginning, and also playing with different UDFs and different functions. And in all scenarios, it showed that using functions and the cost model, given it the opportunity to optimize the query based on the metadata it receives from the statistics, helped cut the runtime pretty extensively. And yeah, definitely shows. The only one that was a little bit close is about the Black Friday data, and that's because the cardinality of the data was so big, so it couldn't really do a lot of optimization about it. But with the user list and user filters and the rest of the data, the cardinality wasn't huge. It wasn't like full strings of whatever. And then it really showed up how efficient it is. So there's a lot of tools, and there's a lot of more information of how to work with Apache Spark. And every time there's new version, there's always new updates, there's always new things. Just make sure when you're working with it that you actually configure it to use the new feature, because most of the time when they send it out, even if it's a new version, they disable the new features because it's still considered under experiment. So a little bit like the cost model where it's disabled, see if you want to try new things and just make sure you're enabling it. And of course, there's a lot of more tools. I often use the IntelliJ tool plugin where I can submit a Spark job from IntelliJ direct to the cloud. It's out of the box and configured to work with Azure, but you can configure it to work with your cluster or with your cloud. It's open source, so you can do whatever you want with it. And then there is the Spark remote job about how you can launch a remote job basically into and create your own HTTPS server with Spark, so you can connect it with a lot of different features. And some takeaways. So use UDF as a last result, only if you have to, only if there's no other way. Most of the time, when we take the functions we want to run, we can break it into smaller functions, and then it's going to fit us into the functions that already exist. So that's a really good thing to do and best practice. Also, UDAF. UDAF are also expensive because they hold everything in memory. Every time they get a new entry, often they calculate everything from the start. If you have an array or if you're having some collections there, see what happens to the memory and see what happens to the disk and those kind of stages, and you'll notice that there's peak in the memory that it consumes for every entry, because it calculates everything again. So notice that, and if you can break it into functions, definitely go for it. Gather statistics for the cost model. Best practice to do about it, it's always have some cron job running in the background, collecting all the statistics. So once you actually trigger a Spark job, it's already have the statistics and you don't need to calculate it on the fly. Especially important if you want to work within a streaming application. If you're doing near real-time or real-time processing, you definitely want to have those statistics always available for you and not something that you calculate only when you're using Spark. And look under the hood, see what you're doing, understand what's going to run, understand the filters, understand the optimization, and also, if you would like, look inside the code base. Really interesting how they implemented things. You learn a lot of stuff that doesn't exist in the documentation. And thank you.
Παρακαλούμε. Εμείς ευχαριστώ. Do we have any questions for Adi?
How demanding in terms of storage is the analyze operation?
How again, sorry?
How demanding is depending on storage and or CPU time, the analyze operation is?
Mm-hmm. So I'm just going to repeat the question. What's the stress on analyzing the storage when we run it? So it depends on the storage. Some storages are already optimized. So if I'm looking at columnar storage, like Parquet, like all this kind of stuff, they already have the statistics. They already calculated. Every time they write an entry to the database, they update the statistics, so it's on the fly, you don't feel it. So what they do is basically they send it to Spark, and Spark calculates whatever it needs from there. But it depends on the storage. I used to work in a company where we implemented our own storage, and there you need to be careful, because if the statistic about specific file is bigger than the actual file, you don't get any optimization. So definitely, see what kind of storage you're working with. Make sure it collects statistics, because it's really going to help with the cost model. And the team in Databricks and Apache Spark are really investing in the cost model, making it even better and better in every version. And yeah, have a cron job, make sure everything happens and update it.
Thank you. Any more questions? No?
Is Cassandra such a model?
So does Cassandra have statistics on the data?
Yes.
So Cassandra has something, but it's unstructured data. So by default, it doesn't hold a lot of statistics. I don't know about the new version. I know about the version before, like 3 years, 4 years, something. So I guess as long as the big data word process, people understand that they need to hold statistic about the data, because they can't really scan everything. They need to do some guessing in a way, some understanding of what exists there before they go and scan all the data. So I guess Cassandra is not different, and they're also probably following everyone else in the market.
And one last question. Anyone? So a big round of applause for Adi, please.
Thank you.
Thank you.